Hello, good morning.
Good morning, sir.
Good morning, sir.
Good morning,
So,
sir.
good morning. So, in the last class, what we have done, can anybody just give a brief summary of what we have done in the last class?
So we were working on Alamoti code. The transmission part, we compared the bit error rate for Alamoti and the multi-antenna system.
We studied the Alamouti scheme. We studied Alamouti scheme and the advantages. We do not require CSI at the transmitter. So that is why Alamouti scheme is preferable because it does not require the channel status information. And what is the generalized version of the Alamouti scheme? Do you remember? What is the full form of this? Space, time, block codes.
Time block code.
Space, time, block codes. And it is also called orthogonal. Is my voice clear to you or not?
Yes, sir, it's clear, sir.
Yes, sir.
And why do we call it orthogonal?
So the
Because
signals transmitted.
if you remember the columns which we achieved after doing some algebraic manipulations, we have seen that these columns were orthogonal. What is the definition of orthogonality? Correct? And if it is, this is the condition for orthogonality, and if this is also satisfied, this is called orthonormality. But I don't think it is satisfied here because it was norm of H. So it is orthogonal only. And why did we call it space-time block codes? Because if it is two antenna, then in the first time slot we transmit x1, x2, and in the second time slot we transmit this. So whatever input stream is coming, we now code it in both space means antennas, and in time, because we transmit x1, x2 in one time slot, and we transmit this in the next time slot. That is why it is called orthogonal space-time block codes. And we studied that BR performance of this by knowing that MRC, we have to replace P by sigma square by P by 2 sigma square. Correct? Is this clear? Whatever was the performance of MRC, you have to divide it by P by 2 sigma square. I mean, you need 3 dB more power to have same bit rate performance at high SNR at least. So these are the things we discussed in the last class. So let's start with a new topic, that is singular value decomposition. Do you know what is singular value decomposition from your other courses?
No, sir.
The concept of singular value decomposition says that a matrix H, such if it is R cross T and R is greater than or equal to T, we can decompose it in this form: U sigma V Hermitian, where U will be a R cross T matrix, sigma will be a T cross T matrix, and V Hermitian will be a T cross T matrix. Effectively, it is a R cross T matrix. And what is the structure of U? U will have columns, T columns. Sigma will have diagonal elements, and V Hermitian will have a row form like this. Such that the following properties are satisfied. First properties, what are the properties of each U, sigma, and V? Properties. First, U Hermitian, U is an identity matrix. What does it imply? That U is a orthonormal. U has orthonormal columns. Just see this. Do you follow this or not? If I say U Hermitian U is equal to identity matrix, it means U has orthogonal columns. Can you prove that? So if U1, U2, this is a U matrix, for example, and I say U Hermitian U is identity. So it means you can write U Hermitian like this, and you can write U like this. Just product, just multiply both of them. What you see, U Hermitian U1 is U1 first element will be this, second element will be this, third element will be this, and the fourth element will be this. And we say it is an I identity matrix. This implies if T is equal to 2, for example. So what does it mean? It means U1 Hermitian U1 is equal to 1. U1 Hermitian U2 is equal to U2 Hermitian U1 is equal to 0. And U2 Hermitian U2 is 1. So this is the condition for orthonormality. What is the orthonormality condition? Tell me anyone. When two vectors U1 and U2 will be orthonormal, when U1 Hermitian U2 is 0, or U2 and U2 Hermitian U1 is 0. This is called orthogonality. And if U1 Hermitian U1 and U2 Hermitian U2, that means norm of U1 square, norm of U2 square is also 1, then it is called orthogonal, right? Orthonormal. So this is the orthonormality condition. U1 and U2 are orthonormal. Clear? So U1, all the columns are orthonormal. Or you can write it in a precise form. U Hermitian U is identity matrix. Second, V Hermitian V is VV Hermitian. Is equal to identity matrix. And this is called that V is unitary. So V is also satisfying that orthonormality condition, but we are not seeing the columns because we are more focused on its rows. So it is a V is a unitary matrix, you can say. But it is also satisfying that condition that V Hermitian, its all columns are orthonormal, also orthonormal. But it is also satisfying this condition, correct? That you can reverse the order of V's. The third condition which this type of decomposition satisfies, that sigma is a diagonal matrix. And this diagonal matrix, the diagonal entries are singular values of H, because we have decomposed our H in this form. So the entries of this sigma matrix are singular value of the matrix H. And we always write, if this is the singular value, sigma 1, sigma 2 up to sigma t, we always write it in this form, in the decreasing order. And the number of non-zero singular values is rank of the matrix H. So what we have seen, that we can decompose any matrix of R cross T in where R is greater than or equal to T in this manner: U sigma V Hermitian, where U has columns which are orthonormal. Sigma has a diagonal matrix where the entries are called singular values, and we always arrange them in the decreasing order. We satisfy unitary condition that V Hermitian and V Hermitian V is identity. And further, number of non-zero values as sigmas are called rank of the matrix. So how to evaluate singular values? Generally, I assume that you know, but I will take an example of orthogonal matrices where it is easier to evaluate singular values. Otherwise, singular values are, do you know eigenvalues? No? Do you know eigenvalues? No? Anybody? Eigenvalues? Pritha?
So we have studied, but I can't remember the points.
Okay, so eigenvalues are nothing but, if you remember, if you have to solve it like this, the solution of this is called eigenvalues, right? If A is a matrix, where A is a square matrix, so eigenvalues are defined only for square matrix. But since we have shown that H is our R cross T, so in that case, what happens? We take eigenvalues of this matrix. This is a square matrix, right? T cross R cross T, it's a square matrix. So eigenvalues of this matrix are nothing but singular values of this. So this you have to see first. I mean, what is the eigen? I mean, I will just post some PDF or something how to evaluate the eigenvalues, the singular values for any matrix H. But as far as I remember, this eigenvalues of root H Hermitian H, if I remember it right, it is called singular values. Just I will post some PDF, because our aim is not to evaluate singular value decomposition for each matrix, and I assume that you have studied in your linear algebra. So I will just discuss here few eigenvalues of orthogonal matrices. So let's try to find out if your matrix is like this. Is this an orthogonal matrix? First check. Because its columns are orthogonal. Correct? Anybody? Pratha?
Yes, sir.
Just let me know if you do not follow anything or anybody. Atharv and
Yes, sir.
Himadri. So just visit the concept of singular value decomposition. How to evaluate singular values of any matrix? It is eigenvalues of square root of A transpose A or A Hermitian A. Okay? And eigenvalues is nothing but solution of determinant of A minus lambda I. So, but that is a little tedious to evaluate the singular value of any matrix. So here we take a particular example of how to evaluate SVD of orthogonal matrices. So any matrix H of this form is a diagonal matrix. So because diagonal matrices are always orthogonal. So diagonal matrix, this H can be written like this: identity, and this matrix. Now our aim is, what was our aim? To write H in this form. Correct? So as you see, this is a form of sigma. But the only problem is, and this satisfies the orthogonality condition, that both the columns should be orthonormal, and this also satisfies that condition. But the only problem is that the order is not right. I told you that the order of the sigma should be sigma 1 should be greater than or equal to sigma 2. So root 5 should come here. So for this, what we can do, we have to first swap the rows or swap the columns. First swap the columns and then swap the rows. So for this, what happens if we just swap the columns of the or rows? Okay, swap the rows first. If we swap the rows of this matrix 0, root 5, 1, 0, what we have to do? We have to swap column of this matrix. If you see, the product of these two is same as product of these two. That is why when I am flipping the rows of this matrix, I am flipping column of this matrix. Just multiply and see. And then what we have to do? We have to write it like this, because we have not done anything for this matrix. Now we have to flip the columns in order to take root 5 here and 1 here. So when we flip the column of this matrix, middle matrix, we have to flip the rows of the right matrix. This is a little trick which is used in order to find the SVD, singular value decomposition for orthogonal matrices. So go to previous 0, 1, 1, 0, and because we have flipped the column of this, we have to flip rows of this. So it will become 0, 1, 1, 0, previous, and we have flipped 5, 0, 0, 0. Yes. So this is the singular value decomposition for this matrix H. And where singular values are, first is root 5 and the other singular value is 1. Is it okay up to this point? Or any doubts?
Sir, why are we doing these calculations?
Because I told you that this type of decomposition is satisfying every property of SVD, but the only problem is the order, that root 5 should be here, because the properties is SVD is we always arrange these singular values in decreasing order. So in order to take root 5 here, what we can do? We have to do some rows operation and the column operations, right? So root 5 first will be moved here. So first we do row operation. So row operation means we have to swap these two rows. And once we swap these two rows, what we have to do in order to make the product of these two constant, we have to swap the columns of this matrix and just multiply it. And you will see that, okay, just take any example. Just tell me any two matrix, not necessarily. Okay, just take 1, 2, 3, 4, 0, 1, 2, 3. So what is the product of this matrix? 4, 1, 6, 7, correct? 3, 8. Okay, now we say we have to flip its rows and we flip its columns. Let's see what happens. 4, 7, 8. See, the matrix product is same. So once if we swap its rows, we swap the columns, because the product is like that it is like column into rows in some. So that is why if you do so, the product is same. So it does not change anything. And next, what you have to do in order to bring root 5 here, you have to do the column operation. And what happens when we do column operation? If we swap the columns of this middle matrix, and if we swap the rows of the other matrix, the right matrix, the product is same. So now you have converted in the standard SVD form. That is why we have done this. Now is it clear? Pratha, still difficulty? Okay, Pratha left. Atharv, is it still difficult, this concept? Himadri?
No, sir, it's clear now.
Okay, thank you. So let's do one more example. Just, I think, yeah, take a one example like this. So this is also an orthogonal matrix. Just check if this is orthogonal or not. What is the condition for orthogonality? C1 Hermitian, C2 must be 0. So it is an orthogonal matrix. So let's do its SVD. For this, what we do? We first normalize these two columns. What is the magnitude or norm of this column? Himadri? What is the norm of this column? Correct?
Under 2.
And 2 root 2. Now I tell you the steps. First, normalize each column. And what is the normality? The norm of each column, just put it in the row, in the column, in the diagonal form, like this. And then what you do, you divide each column by its norm. So now these columns are orthogonal as well as orthonormal, because we are taking orthogonal condition, but this because you must also satisfy orthonormality, that each column must have a unit norm. So we divide each column by its norm, and whatever we have divided, we have just written in the diagonal form, so that this is same as this. If you multiply these two matrices, it will be same. Now, if we just put an identity matrix here, it will not make any difference, because our multiplication of identity with any matrix is same. Now we have to do the same thing. What we have to do? We have to check the order. Order of the singular values should be like this. It should be arranged in a decreasing order. So 2 root 2 must come here. So for this, what we have to do? We do first row swapping and then the column swapping. And when we do the row swapping, we have to swap the column of this. So when we do the row swapping, okay, we can write its column 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2. We have not swapped yet, but just simplified the, yeah. So now just swap its rows and swap these columns. So once we swap the rows, 0 to root 2 will come above and root 2 comma 0 will come in the down, and we have to one by root 2, 1 by root 2. Correct? Is this clear?
Yes, sir. Yes,
And
sir.
now what we have to do, we have to swap the column. And once we swap the columns of the middle matrix, we have to swap the rows of this. Correct? So swap the rows. It's just a shortcut method. Otherwise, you have to follow a procedure, which we are not discussing because our aim is just to find out singular values, which we will use in order to find the capacity of the MIMO channel. This is our final aim actually. But just we have introduced a little concept of singular value decomposition. So this is your H matrix now is decomposed in singular values. It is satisfying all the conditions. So what are the singular values? 2 root 2 and root 2. So singular values are easy to derive. Just if the matrix is orthogonal, whatever is the norm of each column is the singular value. Correct? Now let's see what is the application of, because this is a MIMO, we are discussing MIMO. What is the application of all this in MIMO? So if you are receiving this type of vector, is this clear? This is a MIMO system. This is R cross T vector where R is the receive antennas, T is the transmit antennas. Sorry, this is R cross 1, R cross T, T cross 1, and it is also number of receive vector. Yeah. This is clear? Is this notation, are you familiar with?
Yes, sir.
Okay. So now we have told you that any matrix H, if R is greater than or equal to 2, can be written in this form, can be decomposed in this form. So can we just replace H by this? So now this is your effective received signal or effective channel model. And if you know your H both at the transmitter and the receiver, if you know your H both at the transmitter and the receiver, you can do something very interesting, which will change your channel, MIMO channel, into parallel channels. See, if at the transmitter, what you do, you just multiply this at the receiver, you multiply this with U Hermitian. So U Hermitian, U is I, you know. And at the transmitter, you transmit X is equal to V Hermitian X tilde. If X tilde is information vector, we first multiply it with V Hermitian and then we transmit it. So you can think it like that. This is X Hermitian. You multiply it with V Hermitian. This is your X, which you using multiple number of antennas. This is a T cross 1 vector. You have fed it to each antenna and you transmit it. And this is a 1 to up to R number of antennas. So each antenna will receive some copies from each antenna, right? If this is X1, each antenna will receive h1 x1 plus h2 x2, something like that, right? Some portion of this signal, some portion of this signal. But if you do something interesting, you can convert this channel into parallel channels. So what this is the main reason for doing SVD. So just see here what we have done. We said that we first multiply your x tilde to V Hermitian and then we transmit it. And then here we multiply with U Hermitian. So we have already multiplied with V Hermitian and we've seen that our signal is sigma V Hermitian x hat plus x. And x is nothing but x tilde V Hermitian. Excuse me, I have done something wrong, I think. Yeah, it should be V, not V Hermitian. Because V Hermitian is already here. So this is nothing but U Hermitian Y, sigma V Hermitian V is identity. So this is nothing but sigma x tilde plus n. So now you see that you can write this signal, effective signal R, effective received signal R as sigma 1 0 0 0 sigma 2 0 0 up to sigma t x1 tilde up to xt tilde plus n1 tilde n2 tilde up to nt tilde. Why I am taking tilde here? Because I have also multiplied. I just forgot, because when you multiply your y with U Hermitian y, you have to also multiply with U Hermitian. So this is your new n tilde. And this is yours. See, now you have your R1 as sigma 1 x1 tilde plus n1 tilde. R2 is sigma 2 x2 tilde plus n2 tilde. Sigma R sigma t xt tilde. Is this clear? That if you are using T number of antennas at the transmitter and R number of antennas at the receiver, each receiver will receive some x1 and x2, the superimposition, the addition or superimposition of superposition of x1 and x2 up to xt. So it is like if you want to extract x1, it also has mixture. This we receive mixture of all x1, x2 at each antenna. But if we pre-process and here we do some post-processing, now what we have done, we have extracted this mixture of x1, x2, x3. Otherwise, we would have received a mixture of all these x's at each antenna. So this is what we have done. So the concept of SVD is used here in MIMO setup in order to convert a system, a MIMO setup, into parallel stream of CISO setups. Now is it clear? If there is any doubt, you can ask.
Yes, sir, it is clear.
Otherwise, you can take a simple example of a 2x2 or 2x3 MIMO setup or 2x2 MIMO setup. And you see that if it is our setup, so if we transmit x1 from here, x2 from here, and we transmit, what we receive, y1 is nothing but x1 plus h11, sorry, h11 x1. What we receive, h11 x1 plus h12 x2 plus n1. And y2 is h21 x1 plus h22 x2 plus n. So see, the each y1 and y2 have a mixture of x1 and x2. So it is difficult to process, right? Because you have to either jointly decode it. So it is difficult. But if you want to simplify it, we do some pre-processing. And the post-processing, if you know the channel both at the transmitter and at the receiver, something like that. And what you will receive, x tilde, you will receive your y1, or after the processing, your r1 will be some sigma 1 x tilde plus n tilde, because the I'm just writing n tilde here. R2 is sigma 2 x tilde plus n tilde, where sigma 1 and sigma 2 are nothing but the singular values of channel matrix H. In this case, channel matrix is. So in this example, where we took this channel matrix, what is the what would be your R1 and R2? Your R1 will be 2 root 2 x tilde plus n, and your R2 will be root 2 x tilde plus n. Correct? Since these n's all have a same normal 0 sigma, both in phase and quadrature phase with 0 and sigma square, we just write it like this. Either you write tilde or you write n, doesn't make any difference. So now you have seen that you have converted your mixtures, you have extracted, right? So it is simpler to. So T parallel wireless channels. This is called multiplexing, spatial multiplexing. Why do we call it multiplexing? Do you remember the concept of multiplexing? This is the concept of multiplexing, that you first transmit the mixture of a signal from a wire, and here you demux sort of thing in your electronic system, and it give you the same stream which you have transmitted. They do not intermix with each other. Similar concept is happening here. You are transmitting a x tilde vector, which is x1 tilde, x2 tilde, right? We just, sorry, here I should write x1 tilde, sorry, excuse me. Correct? So there are two parallel streams of wireless channels. Up to this point, it is clear, or I have to explain it a little more? Just tell me. Just take 2 minutes and think. Athar? Himadri?
Sir, can you please explain the last thing again?
Which
The
one?
concept of multiplexing you were saying.
Okay, so multiplexing you might have heard in the digital electronics, mux, demux. And just
Yes,
saying, what is the muxing? You send bits from here, right?
Yes, sir,
And
multiple.
yeah, and here you demux it, like whatever 1010 sent here, it comes here. So I'm just relating this concept of here from your knowledge of digital electronics, just like that. So it is like that is why it is called spatial multiplexing. I'm just saying, because you are doing something like that only, right? Because in the channel you transmit this, and at the receiver you are having this, right?
Yes, sir.
X1 tilde
Yes.
does not affect X2 tilde, and X2 tilde does not affect X1 tilde. Correct?
Yes, sir.
That.
Yes, sir.
Now clear?
Yes, sir. Thank you, sir.
Yeah, it's okay. Welcome. So we have done this up to this part. So now the question is, what is the capacity of this MIMO wireless channel? So now we have T streams. Just remember, we will have T streams, not R streams. T is the number of transmit antennas, because we have done some processing. This is the concept. This is the basic understanding, that even if you understand what I'm saying? Here, what are the number of R's? It is T. T cross 1.
Yes. Yes, sir.
But the received signal, what R? So even if your R is not equal to T, even if suppose you are using this type of setup, and you are doing SVD concept, you are post processing, and peak processing, and your post processing, you are sending 2 bit, right? Two streams. So you will receive 2 streams only. Okay. Is this making you confused, or are you clear? Because the processing is done like that, right?
Yes, sir.
Okay, great. Just you will do one example, then you will understand. And we say that each stream has power Pi. So there are T parallel, you can understand it like T parallel seesaw channels between transmitter and receiver. So what is the Shannon rate of the channel? What is the Shannon rate of a CISO channel? If you remember, the capacity log to 1 plus received SNR. Do you remember? This
Yes,
concept,
sir.
do you know? Okay.
Yes,
So
sir.
what is the SNR, received SNR for this case? Sigma square EXI square by sigma square. This is sigma square is different than this sigma square. Okay, don't confuse it with. This is noise variance, and um, this is your singular value. Correct. So what is this? This is sigma square pi by sigma square. And what is the, and one more thing we have to see, that we are putting a constraint on the total power. Like if you are using 3-4 bit streams, each with power P1, P2, P3, P4, what is the total amount of power which must be transmitted from the antennas? So the total power is I is equal to 1 to T is P. Okay. Total power radiated into the channel using multiple number of antennas is P. Is this clear up to this point?
Yes, sir.
Okay, less than equal to, you can say. So this is sum rate. So what is the sum rate? This is for one CISO channel, the total, because we are having N or T parallel channels, the total sum rate is this. Total sum rate is this, and the constraint is this. So what? How do you write constraint? Subject to, right? So our problem is, if we want to derive what is the capacity of a MIMO channel, capacity of a MIMO channel, when you know your H both at the transmitter and the receiver, since you know both H both at the transmitter and receiver, you apply some SVD concept, and you see you have converted to parallel channels, and the sum rate is, because you know what is your capacity, what is the maximum possible sum rate under the constraint, subject to sigma pi is less than or equal to p. So our aim is to find out what should be the values of power, what power we should insert in each stream, which maximizes your capacity or total sum rate, which maximizes your total sum rate. This is your sum rate, right? So because we don't know the power of each stream, we just know that there is one constraint, that total power should be less than or equal to P. So how should we choose this Pi so that the sum rate is maximum? That is called capacity. Is this okay up to this point?
Yes, sir.
Okay. So this optimization problem or constraint optimization problem, this is constraint optimization problem. And it can be solved by using Lagrange multiplier method. Lagrange multiplier method is used in order to solve such problems. So what is the objective function? If you solve a optimization problem, you always write objective function. So objective function for a Lagrange multiplier problem is written like this. This is your maximization problem. This you want to maximize, right? This thing you want to maximize under the constraint this, right? So we write it like this. Plus lambda times p minus I is equal to 1 to t pi. This is your constraint, right? So we just take constraint here, p minus sigma pi. This is the way we formulate objective function for the Lagrange problem. We just write first the function which we want to optimize or maximize, and whatever is the constraint, we multiply it with a Lagrange multiplier. and the subject to condition is written like this. So this is the objective function for the Lagrange multiplier case. And in order to solve that, how if we want to maximize this, we have to first differentiate it with respect to each pi, because we want to find out what should be the value of each pi which maximizes this objective function. So first we have made a Lagrange objective function, and then we differentiate this function with respect to pi, each pi. Just let me know what should be the value of this. If you differentiate it with pi, just tell me what should be the value of this function. Athar? Himadri? Just try it. Otherwise, I will tell. Don't worry. This is pi, sir. This is
1 by
now correct. 1 by
summation.
see
1 by
this
1.
you can think of like it is a p1 and p2. All the other will be 0 because you are only differentiating with pi.
Yes, sir.
Since suppose you have t is equal to 2, then there will be p1 and p2 only. But since you are
Yes, sir.
differentiating with ith, all the other will be 0. Correct? I am just neglecting
yes,
that
sir.
because ln is 1 by x, so you have to also multiply with log. So I am not bothering about that. Okay, you understood what I said? Ln x is 1 by x,
Yes, sir.
and log 2 you have to appropriately adjust. So that I am not bothered about because that will not. So this is, and now you have to differentiate it again.
Sigma I square upon sigma square.
Now what is the
Yes,
differentiation of this? Let me know. This is constant, it will be 0. And here, what will you have? Sorry, 1 only.
Pi 1 1. Yes, sir.
So what should be the value of lambda?
Lambda is
Because we'll have to
equals
equate
to
it to 0. What should be the value of lambda?
1 sigma I square upon sigma square into 1 upon 1 plus sigma I square pi upon sigma square.
Okay, what should be the value of lambda is? Lambda is 1 upon
So
1
this-
plus sigma I
Yes,
square
so this
pi
whole
by
term.
sigma. Yeah, sure. Correct?
Yes.
So what is the value of 1 over lambda?
1 plus sigma I square.
Correct? 1 over lambda will be
Yes.
this because we have just multiplied it. But
Yes,
one
sir.
more thing you should understand, that this implies what is your pi? Your pi should be this. So our objective was to find out what should be the value of pi's. Correct? Under the constraint sigma pi is less than equal to p. So the one more thing you should understand, the power cannot be negative. So we take this, which says whenever it is 0, don't put negative, don't put any power in that stream. Because power cannot be negative, right? If your answer of this, you solve it and your answer is something -1, you say that power cannot be negative. So you have to put it 0. So this is the one thing you have to understand or remember. That power at
Yes, sir.
ith stream is this. And now, because you know the constraint which says it must be sigma pi is equal to p, you put each value of I here, which you have derived, which you have achieved or obtained. So from here you will get the value of lambdas, and for then you replace your value of lambda here and you get value of pi. So this is the procedure. And this is called, see, the final is just solve this problem. Just solve this. Whatever lambda you get, you put it here. 1 by lambda minus sigma square by sigma square. So our objective is to solve this. And this problem is, when we solve it, is called water algorithm we use is called water filling algorithm. And why we call it a water filling algorithm, we will take it with an example. We'll understand this concept with an example. So can you summarize what we have done till now? That we are trying to find out the capacity of a MIMO channel where the channel is known both at the transmitter and at the receiver. And we said if the channel is known both at the transmitter and the receiver, we will post-process and pre-process using the concept of SVD, and it will convert your MIMO channel into T CISO parallel channels. And each CISO parallel channel has a capacity of log 1 plus sigma square I by pi by sigma square. So what is the total sum capacity of this system? This is the total sum rate of the system is called, if you maximize the total sum rate of the system, is called capacity, and under this constraint. So this is the main summary of this lecture. Now we have just told you that it is called water filling algorithm in order to solve this problem. This is the final solution. It says you choose lambda from solving this, and whatever lambda you get, you put it here, and you will get the powers, because the aim is how to assign power to each stream, which will optimize or maximize the total sum rate, right? Just let me know if anything is confusing or ambiguous. So
Sir,
let's first start.
yes, sir.
Yeah.
Can you please give an example for
Correct.
the
That is what the
previous?
main aim, because otherwise it will be difficult.
Yes,
So
sir.
just take a 3 cross 3 H. Okay. So what is the singular value of this matrix? Tell me. Only the singular values. I told you how to first check it is orthonormal or not, orthogonal or not. It is orthogonal because if you just see orthogonal, the columns are orthogonal or not. Check it, Himadri. Quickly check. Himadri, have you checked? How to check if the columns are orthogonal? C1, C2, C3. C1 Hermitian, C2, C2 Hermitian, C1, C3 Hermitian, C1. All the combination must be 0. So just do it. So it is zeros, okay? If you see Ci, Hermitian, Cj are 0. Columns are orthogonal. So what I told you, just first evaluate the norm of each column. This will give you singular values. For the orthogonal condition only I am discussing this, because I told you otherwise evaluating these singular values are little different. So we will discuss it in the next class, or I will just tell you an example by taking an example. Here till now just understand for the orthogonal matrix only, and the singular values are simpler, which gives you the norm of each C2, C1, C2, C3. So just evaluate the norm of C1, please.
Root 13.
Great. What is the norm of C2?
Root 52. Sir, I will calculate.
What is C3?
2.
So sigma 1, what should be the value of sigma 2, and sigma 3? Because it should be in the decreasing order, sigma 1 should be root 52, which can be also written as 2 root 13. Sigma 2 is root 13 and sigma 3 is 2, correct?
Yes, sir.
So this is your sigma 1, sigma 2 and sigma 3. So if you do all the processing which we have discussed in the class, because this is your H, so what should be your Y? But I told you that you know this sigma This H can be written like this. And because you are doing the post-processing as well as pre-processing, you will receive some R of like this. This
Yes,
is
sir.
I, this is I. Now, how can you write your effective received signal? Your R1 and
R
R2 is
Ri is equals to
sigma 1
X
X1 tilde plus NT1 tilde.
and
Singularly. Correct? So this is your received signal. That is not the objective. Objective is to find the capacity. Correct?
yes,
What
sir.
is the capacity? Summation of log
Log
2 1
base
over
2
sigma square by sigma
1
square
plus
pi.
sigma square pi upon sigma.
We want to solve this, right?
Yes, sir.
In order to get the capacity, we have to solve it. So just try to solve it. We said 1 upon lambda minus sigma square by
Sigma
sigma
upon sigma.
sigma I square. I is equal to 1 to 3 because we are taking 3 examples. Should be equal to P. Correct? And plus. So just assume that your noise variance is 1 and your total power is 3 dB. 1 watt and your total power is 3 dB means 2 watts, right? Is this okay?
Yes, sir.
Okay. So I am not doing the steps how you get your R's. You can do it, right? I hope. Can you derive the U and V from this H? You have to, what you have to do? You have to first write it in this form. Okay, so water filling we will do, I think in the next class. Before that, I will just tell you how to convert into U and V, right? Because you have to convert, you should also know that we can convert into this form, right? Because if you
Sir,
want to
can
do
you
the
please
process,
explain how?
okay, you want to know, okay, please.
Yes.
Just do it that first, huh? 2, the matrix is, what was the matrix? Can you tell me? 2, 3, 0,
0
minus 6, 4,
minus
0,
6 4 0 0 0 2
and the
root
norms are.
2 root 13 and 2.
So what did I tell you? If the matrix is orthogonal, we have checked it is orthogonal. Whatever is the
Yes, sir.
norms of each columns, we first organize it in this way.
Yes, sir.
And we write the new columns, the normalized columns here.
2 by root 13, 3 by root 13.
Minus 6 by
6
2,
by
13,
root 2
4
root
by
13.
2, 13, 0, 0, 0, 1.
Yes, sir.
And here we multiply it with identity because
1
it does not.
0.
Now the only problem here is that you have to write your this matrix in this form. So you have to do row swapping and column swapping, or row flipping and column flipping. So first you have to take it here, for example.
Sir,
Right?
when we can find the sigma 1, sigma 2, sigma 3 in increasing order directly, then why are we doing these steps?
See, if you want to find out the capacity, then it is okay. You can just, you have sigma 1, sigma 2, sigma 3, and you can directly go to this, which I called, it is called water filling algorithm, which I will
Yes,
tell
sir.
you how to solve this. That is in order to find the capacity. But if somebody asks you, what should be the value of the pre-processing matrix and the post-processing matrix? Understood?
Yes,
Because
sir.
I told you
Yes, sir.
what should be V if you're X tilde and this is your antennas and this is your receive antennas. Here you multiply it with U Hermitian. What should be value of V and U? Then you have to do the step, right?
Yes, sir.
Because I told you the SVD has this form where sigma must be, these U sigma V Hermitian must satisfy some properties, and all we, because H is orthogonal, it is simpler that now we have derived that okay, U is satisfying the property. We said, but we have to just do the operations over rows and columns in order to satisfy
Yes,
this
sir.
property. That is why I am
Yes,
doing
sir.
all of these things. Okay. So just do the row flipping for this.
0 to root 13. 0, 0.
And when we do row flipping, we have to do the column flipping here.
Yes, sir.
So whatever
Mine-
rows you have flipped, you have to
Minus 3 by root
column
13.
C1, C2.
Minus
Great.
3 by
2 by
root
2 root 13, 0.
minus 2 by
2 by root 13, 3 by root 13,
3 by
0,
root
0,
13,
0, 1.
0.
Now what we have to do, we want to take this here and this here, right?
Yes, sir.
Column swap. So if you want to do the column swap, you have to do the row swap of the
Yes.
right matrix. Just do it. So your new matrix will be like 0, 1, 0, 1, 0, 0, 0, 0, 1. So this is your V Hermitian. And this is your U Hermitian. Sorry, U. And this is your sigma after the. Okay.
Yes, sir.
So now you know what should be the pre-processing matrix, post-processing matrix, and what are the values of sigma 1 and sigma 2. So the first condition, first step is completed. Now you can design your transmitter and receiver for in this case. Now your objective is what should be the powers of each stream. How should you give power to each stream? That is your because you know, I mean, what should be the pre-processing and post-processing matrix? That is okay. That is very good. That now you can convert a parallel mixture of all signals into parallel channels. But further, you want to optimize this system by providing optimum powers to each stream, which will give you the capacity or maximum sum rate. So this is the next objective. Now I hope I make more sense, right?
Yes,
Now you
sir.
know this, know this. Now you should know what should be the value of each stream which is coming here. X1 tilde, X2 tilde, up to Xt tilde, right? What power we should give to each. This is the objective. So we discussed that we should solve this problem. This is called, and using water filling algorithm. So do you want to do it today or in the next class? Because 12:10, I think it will take time to, it will not be finished. So if you want to ask any question, you can ask from the previous lecture or today's lecture. We will solve this in the next class, the water filling algorithm, and we will just want to find out what should be the P1, P2, and P3. And corresponding,
sir.
we will find the capacity. We'll find out P1, P2, P3. If total power is 3 dB, if you are given 2 watts power, what should be the value of each stream? How should you locate power to each stream which maximizes this? And we will see this in the next class. I think that will be better because 12:15 almost already. So just ask a few questions if you have any doubt, anything in your mind.
No, sir, no doubt yet. But I will go through this lecture, and if I will have any doubt, then I will mail you.
And also try to see the similar value decomposition for any arbitrary matrix. Okay.
Yes, sir.
And Athar is also there or he left? Athar, do you have any query? No, I think Athar is also not having any query. So we will do this water filling because a little lengthy and involved process, and we will do it from the fresh mind. Okay.